Our last talk for today is talk by Mukherjee from Tata Institute of Fundamental Research, and he'll talk about correspondences on compact Riemann surfaces and combination theorems.
Thanks, Tanya. Yeah, this is on, right? All right, let me first thank the organizers for inviting me, for putting up this conference. Right, so I'm going to be talking about correspondences on compact Riemann surfaces. Correspondences from a dynamical perspective, viewed as dynamical systems, and what they have to do with combination theorems and what's known as Sullivan dictionary, which already showed up a few times. Daniel talked about it. Somebody else talked about it today. Anyway, all right. So what's the main goal here? The main goal is to look at two different classes of conformal dynamical systems, which are given by rational maps on Riemann sphere, and the actions of Kleinian groups, which are discrete subgroups of Mobius transformations, PSL to C, acting on the Riemann sphere. So we all know that there are many results, many techniques that are parallel in the study of these two fields. There are results that are similar. I don't think I want to make a list of the several parallel results. There is, of course, the no wandering domain theorem, the Alfor's finiteness theorem, which is what led Sullivan to conjecture that there is a parallel line or a dictionary. Items here, results on one side of the dictionary often motivates progress on the other side, etc. There are ergodic theoretic similarities, conformal measure, Patterson-Sullivan measure, etc., and various other things. Thurston theory. Okay, but going back in the 1920s, Fatou conjectured or suggested that maybe the dynamics of these two different classes of conformal dynamical systems can be incorporated, can be put in a larger category of dynamical systems known as algebraic correspondences. So why this kind of a suggestion? So let's see how to think of a rational map or a Kleinian group as an algebraic correspondence. And what is an algebraic correspondence? So purely algebraically speaking, an algebraic correspondence would be, this is not going to be useful, particularly useful for our approach, but it's a Zariski closed subset of, say, W cross W, where W is some algebraic variety. So what it looks like is you have an algebraic variety, and you have X sitting inside of W cross W, and you have the projection maps pi1, pi2 to the two coordinates. We often assume that, usually assume that pi1 is, these projection maps are surjective, finite to 1. And then in the definition itself, there is no directionality and there's no dynamics at all. But I want to define a dynamics in this direction, which is basically just going back by pi1 inverse and pushing down by pi2. The simplest example would be just take a complex plane or Riemann sphere here. If you take Riemann sphere, this is basically going to be an algebraic curve. So a subset of C hat cross CP1 cross CP1. And so such an algebraic curve, PZW equals 0, is going to define an algebraic correspondence for us using the following. What does that mean? You plug in a particular value of Z over here, and you look at all those values of W that satisfy this equation. And those are, depending on the degree of Z and W in the polynomial P, Z goes to finitely many values of W, which is exactly what these two projection maps are doing. You look at all those points on the algebraic curve whose first coordinate is prescribed for you. You look at all the second coordinates which arise this way and send it to those second coordinates. And this is my directionality. This is what I'm going to call, this is what the dynamics of an algebraic correspondence is going to be like. This is a multi-valued map. Given a point, there are finitely many forward images. Similarly, you can define finitely many backward images. If you give me a value of W, So Z going to W is my forward dynamics, and W going back to Z is my backward dynamics. The point is, this is what led Fatou to conjecture here, that the world of algebraic correspondences, it contains Kleinian groups and rational maps, and of course a lot more. That's because if you, well, I should say finitely generated, everything is going to be finitely generated. All Kleinian groups appearing in this talk are going to be finitely generated. If I have a Kleinian group that's finitely generated, I can write this obvious algebraic curve where you pick a value of W, sorry, pick a value of Z and send it to gamma 1Z through gamma KZ. Say this is the symmetric set of generators for the Kleinian group, and sending a point to its images under the generators is the dynamics. The action of the Kleinian group. How do you get an orbit under the action of the group? You hit a point by the generators, you hit all the images by the generators again, and so on. That gives you the full orbit of a point. This is an algebraic curve, hence a correspondence in this previous sense. Similarly, if you take a rational map, this defines for you an algebraic curve. R is of the form PZ equals QZ. So this is an algebraic curve. The inverse of a rational map is also easily seen if I just write down this. That means Z equals R of W. This is another algebraic correspondence. So that means algebraic correspondences, at the moment, this is all just a formal setup. There's no reason to believe just because algebraic correspondences contain the class of rational maps and Kleinian groups, there's no good reason to believe maybe that studying these things, one can say that, of course, this is the larger category of dynamical systems, so let's study them. Or one could ask, like Kirill said, is there a better reason to study? Of course, at the moment, it's not clear. Given so far what I have told you, there's no compelling reason to believe that studying the dynamics of algebraic correspondences in their own right will tell us anything new about Kleinian groups or rational maps or about the relationship between them. So to this end, I think the first question that one can ask is, can one construct algebraic correspondences that are neither Kleinian groups nor rational maps, but behave a bit like both? Is there some sort of a combination of these two different classes of conformal dynamical system? Can I construct one algebraic correspondence that simultaneously behaves like a Kleinian group and a rational map? And this is what leads us to combination theorems, which of course has a rich history both in group theory as well as rational dynamics. So combination or mating, which is in a way the main goal of this talk. So the first example of this sort was furnished by Bullitt and Penrose. They wrote down a certain family of algebraic correspondences whose formula I don't remember and not going to be particularly illuminating anyway. It's an algebraic function whose degree in Z as well as in W is 2. It's a one-parameter family of correspondences, but it turns out that members of this family of correspondences combine the action of quadratic polynomials and the modular group. Later on, so when I say quadratic polynomials, I do not really mean all quadratic polynomials or even all quadratic polynomials in the Mandelbrot set. Bullitt and Penrose only managed to handle the real quadratic polynomials, and then there were several later work by Lomonaco and Bullitt who extended it to general quadratic rational maps, etc. But I'm not going to talk too much about this particular family, because this particular family is given to you as an algebraic formula, and for what I want, having a particular formula is not going to be particularly useful. So what is my goal? My goal is to try and generalize it.
What does this mean, combine?
Yes, so I'm coming there. So before I say what it means to combine two things, let's at least dream. So the dream is combine arbitrary function groups with degree D polynomials. Okay. These are all finitely generated function groups. So now, okay, so what does it mean to combine them? So let's go back to the definition. I know that if I have a correspondence given a point Z, I have finitely many values, finitely many images. But apart from some bad points, critical points, etc., by implicit function theorem, I can keep track of this multi-valued map by a collection of local germs. So if you fix a value of Z and you want to solve locally as a function of W, here, if you want to find the value of W as a function of Z, away from some bad points, finitely many, you can find such local germs such that P of Z equals Gi of Z is equal to 0. And those are your local branches of the correspondence. Is that fine? So this just means that if my equation is W minus Z square equals 0, or W square equals Z minus 0, I'm just saying that W is equal to positive square root of Z and negative square root of Z. These are the two local functions. In this case, there are finitely many local germs. These local germs have no reason to be global. If such a germ is global, then the correspondence is reducible. You can factor out, for instance, this is a reducible correspondence. In this case, all the local germs are just Mobius maps. However, it can so happen that, say you have some sort of a topological disk, and one of these germs admits one of them an analytic continuation to this particular topological disk. Maybe it has some critical points. So these local germs, maybe one of them admits a semi-global analytic continuation to a large object, to some disk. And the restriction of this germ, or this analytic map now, on this set is conformally conjugate, say, to some Blaschke product. On the disk. So just the Riemann map conjugates this germ, this analytic map to a Blaschke product. Then you see the behavior of a Blaschke product inside of your algebraic correspondence. It could be more complicated. This D could look like topologically the filled Julia set of a polynomial, and maybe the restriction of Gi to that particular filled Julia set is topologically conjugate to a genuine polynomial action on its filled Julia set. Then you see the action of that polynomial restricted to the filled Julia set inside of the correspondence. So you combine really means that you want to see features of blah and blah. You want to see features of polynomials, you want to see features of a group. This is what it means to see the feature of a rational map. It could be a Blaschke product. So one of the branches of the correspondence admits some analytic continuation to a large-ish domain, and this particular branch, topologically, maybe conformally, is conjugate to a polynomial, to a Blaschke product. Similarly, if you say have a simply connected region, say D prime, where the branches of the correspondence Gi extend as all of them, for instance, or maybe some subset of them, Gi through Gk, G1 through Gk. They admit analytic continuations to this largish region as conformal automorphisms. Then you can look at the group generated by these conformal automorphisms restricted to this domain D. And that's going to be a subgroup of conformal automorphisms of this set D prime. Maybe this acts properly discontinuously on this region, in which case you uniformize it to the round disk, and this is going to be conformally conjugate to a finitely generated Fuchsian group. If you have a correspondence which has this particular kind of a property on some invariant part of its dynamical system, and this property on some other invariant part of its dynamical system, then we say that it combines the action of a polynomial or a Blaschke product as well as a Fuchsian group. Does that make sense? Okay. Yes.
Do you want, in this case, the union of these two?
Yeah. There will be a limit set. Yes. Otherwise, there's some junk. True. Typically, I would want that the union of the region, invariant region where the correspondence acts as this, and the region where the correspondence acts as that is the entire phase plane, the entire sphere, for instance. And this is exactly the case for the bullet pen rose examples. So this would be a mating of Z square with this notation means mating with the modular group PSL to Z. So there's some sort of a region, this red region, and a branch of the correspondence here is conformally conjugate to Z square. And here, there's something similar happens. Just an inverse branch of the correspondence also is conformally conjugate to Z squared. And the outside is a simply connected region. It's a topological disk. There, the branches of the correspondence extend as conformal automorphisms. Acts properly discontinuously, take the quotient of the region by the group generated by these guys, you get the modular surface. Okay. Now, how do we even try to come up with a systematic theory of realizing such streams? We are not yet there, not even close, but it turns out that Fuchsian groups uniformizing genus 0 orbifolds with some conditions, but let me not get into it. Good. I really don't mean all genus 0 orbifolds, but the class of Fuchsian groups that I'm looking at, they uniformize. So these Fuchsian groups, the ones that I'm calling good, they uniformize genus 0 orbifolds, including all punctured spheres, including the modular group, including the Hecke group. You can also allow more, but let me just stick to that. Good in what sense? Good in the sense that they allow us to kind of fulfill this dream. We have a way of combining Fuchsian groups of this kind with degree D polynomials with connected Julius, essentially generic ones.
What does it mean, uniformizing?
It means that if I have a Fuchsian group gamma, then D mod gamma is this guy, is this kind of a genus 0 orbifold. Sphere with some number of points removed, hyperbolic orbifold with some punctures and some orbifold points, finitely many. So if D mod gamma is a certain orbifold, I'll say that this is a Fuchsian group uniformizing that orbifold. Okay. Now, the key point is, how do we even construct such a correspondence? As I said, the tricky thing is, if I try to write down a formula of the correspondence, it's going to be unwieldy. I don't know how to study, this is a mating problem. It's at least as hard as being able to mate two polynomials. Writing down an explicit formula for a rational map is never going to help you. You need to somehow prove some sort of a uniformization theorem. Maybe topologically glue some things together and then try to uniformize it, try to put some complex structure, etc. But the point is, we do not want to do it in one step. We do not want to construct a correspondence because correspondences they have too many branches, right? At every point there are finitely many branches, and it's not exactly clear to begin with how to put all these branches together into a large multi-valued map. We want to first construct a single valued map, a single valued combination, and then to upgrade it to an algebraic correspondence. Where did this idea come from? It didn't come from thin air. It came from the classical simultaneous uniformization theorem, for instance. Or let me write two names which are similar in flavor. The simultaneous uniformization theorem of Bose, which I don't want to say too much, but it basically combines two Fuchsian groups. And the reason why you can do two Fuchsian groups which uniformize the same surface. And you can do that because if you take two different Fuchsian groups in the Teichmuller space of a given surface, then their boundary actions are compatible. There's a quasi-symmetry conjugating one to the other. So you can take the action of the first Fuchsian group on the lower half, say southern hemisphere, and the action of the other Fuchsian group on the northern hemisphere, glue them by this quasi-symmetric homeomorphism, and do the usual measurable Riemann mapping theorem. That's the uniformizing part. So first you construct a topological object by gluing them using a quasi-symmetric map, and then put a complex structure to uniformize it. The same thing can be done for two Blaschke products. So in this dictionary, Fuchsian groups correspond to Blaschke products because these are the objects which leave the disk invariant, completely invariant, in fact. Yeah, I don't know who to attribute it to. The first paper where this is probably written is by it's a short note by Macmillan, but the idea is once again the same. If you take two Blaschke products, let's assume that they have attracting fixed points on the disk in the disk, and you want to somehow same degree, of course, and you somehow want to glue them together into a single rational map. So you want a rational map whose Julia set is a quasi-circle, just like this setup. And you want the rational map restricted to the northern hemisphere to be conformally conjugate to B1 and restricted to the southern to be conformally conjugate to B2. The idea is again the same because these are Blaschke products, say, with an attracting fixed point at the origin. They are expanding maps on the circle, same degree. So there exists a quasi-symmetric homeomorphism of the circle conjugating this to that. So this is the boundary compatibility that you need. You use that to glue these two things. It's basically a welding problem. At the end of the day, these are both welding problem, but in an equivariant fashion. You don't just want to glue two disks using a random welding map. This is going to be playing the role of the welding map. Your welding map has to preserve either conjugate the dynamics of the first Fuchsian group to the second Fuchsian group, or conjugate the action of the first map to the second map. So it's an equivariant welding problem. And here you also have a quasi-symmetric map. So you can do it. Measurable Riemann mapping theorem at the end of the day will give you a rational map that's a combination of B1 and B2. So this is our inspiration. This is where we want to draw inspiration from. We want to do something similar. We want to turn our problem of constructing a correspondence, which is maybe a priori a much harder problem. We want to reduce it to a problem of this sort. We want to start with two dynamical systems. Let's work it out only in the simple case of a Blaschke product and a genus zero orbifold group. So what I want is, I want a Blaschke product acting on the disk, and I want a group gamma, Fuchsian group gamma acting on the disk, and I want to somehow put them in the same dynamical plane. But now the biggest problem is that on the one side, I have a non-invertible dynamical system, which is like D to 1, depending on the degree. On the other side, I have an invertible dynamical system that's not even single valued. So how do we even make sense of putting them together? What is the analog of the equivariant welding problem discussed above? For that, fortunately, there was an unrelated construction of Bowen and series, which helps us. This is something around the 80s. So Bowen and series, they started with a Fuchsian group, and they cooked a map out of it. In particular, so by the way, I should say, so exactly what the map looks like, I'm not going to give you a general definition, but the key point is that when the surface has genus 0 and some nice orbifolds, not too complicated, then the circle map cooked out of the group turns out to be a covering map, and hence topologically similar to the map B. If in general the Bowen series maps that you cook out of the group are discontinuous, and it's kind of discontinuous in the generic situation. Only in some genus 0 orbifold case it turns out to be continuous. So beyond this, you have to work harder. But still, the idea is really useful. So let me just give you an example in the case of, say, a 4 times punctured sphere. So start with a fundamental domain. Too many. Let's start with this fundamental domain of a 4 times punctured sphere. The identifications are these. So you have 3 Mobius transformations, gamma 1, gamma 2, and gamma 3. Gamma 1 pairs this side with that one, gamma 2 pairs this with that, gamma 3 this one. And the group generated by gamma 1, gamma 2, and gamma 3 by the Poincare polygon theorem is a Fuchsian group which uniformizes d mod gamma. But what is d mod gamma? This turns out to be a fundamental domain, and how do you get it? You just glue it. So when you glue this, glue that, you require some parabolicity, of course, impose some parabolicity condition on gamma 1, gamma 2, gamma 3, such that these ideal boundary points become cusps and not holes, etc. But then this is identified with that, this is identified with that. These two are 2 different points. So at the end of the day, you get a genus 0 orbifold, genus 0 surface with 4 mark points, 4 punctures. So in this case, d mod gamma is just a genus 0 surface with 4 punctures. And what is the Bowen series map in this case? The Bowen series map is extremely easy. It's just defined as gamma 1 here, gamma 2 there, gamma 3 here. And in the other pockets, symmetric pockets, it's just the inverse of these guys. And kind of serendipitously, miraculously, whatever, this turns out to be a covering map of the circle. So it is topologically conjugate to the map B. Of course, you may say that I'm not quite working with the group itself. I'm working with a map that I cooked up from the group. It's a piecewise Mobius map. It has something to do with the group. They actually proved that the map is orbit equivalent to the group in the sense that the grand orbits of the map are the same, the grand orbits of this map. Let me call it A, the Bowen series map. The grand orbits of the map on the circle are the same as the group orbits in this case. So the map is not too far from the group, but it's still not the whole group. And the map has something in common with B, namely they are topologically conjugate. They are topologically conjugate. So there are 2 things. First is this doubt that you can cast on the process. Why did I pass to a simplification? And my first answer to that question is that's fine. Let's forget about the whole group. Let's first just look at a single value, because the main point is that I do not even know how to glue a group and a map together. So I want to somehow make them meet halfway, and this is my first step. And hang on, and maybe if you're lucky, then you'll be able to go to a correspondence from this stage later. But for now, let's just work with this simplified object that you get from the group. But the second problem is bigger. The second problem is that, I should mention that if I do not have these sort of punctures, and I started with a genus G surface or Fuchsian group, general compact surface Fuchsian group, then the Bowen series map is not continuous. So there's no hope of doing this particular construction, which is why I'm forced to have punctures in my setup. But as soon as I have punctures in my setup, the conjugation, so this particular map A has degree 5, and suppose that my Blaschke product also has degree 5 in this case. So these are both circle coverings, expansive, hence there is a topological conjugation from B to A, but this is not a quasi-symmetric map. Because this map is expanding. These are hyperbolic fixed points. These are parabolic fixed points. So this map is not expanding, and hence the simultaneous uniformization framework of this Macmillan, the whole measurable Riemann mapping theorem does not work anymore. So I cannot simply, oh, this stays where it is. Okay. This really doesn't go up? No. Okay. Maybe this is fine. Okay. All right. Right. So in order to adapt the standard simultaneous uniformization framework to our case, to our situation, what we want is a generalization of the measurable Riemann mapping theorem. It turns out we don't have to prove it. There is a class of homeomorphisms. I think most people know here. It's called the Wied homeomorphisms. These are generalizations of quasi-conformal maps. They have a similar Sobolev regularity, but the point is that the Beltrami coefficient is not essentially bounded. The Beltrami coefficient can blow up to infinity, can go towards 1, but the region where it goes to 1 has exponentially shrinking area. And the good thing is that we proved an integrability theorem, which says that if you have a Beltrami coefficient which has certain distortion property, the region where the distortion, the dilatation goes to 1 or dilatation goes to infinity maybe, has exponentially shrinking area, then there exists a homeomorphism straightening it, sending this particular complex structure to the standard complex structure.
What is the condition?
The condition is that the area of the region where mu h is larger than k, say the dilatation is larger than k, shrinks like e to the negative epsilon 1 over k or something like that, negative k over epsilon, let's say. Right? That's what you want. Epsilon is small, 1 over epsilon is large, k negative e to the negative that, so it goes to 0. It shrinks exponentially. So the region where the dilatation is bad is very small, exponentially shrinking. So this is what the Wied proved, and now we want to appeal to such an integrability theorem to prove a welding, to prove that these maps are actually welding homeomorphisms. A priori, we do not know that these are welding homeomorphisms, and it turns out that these maps phi, they are not quasi-symmetric. So why is quasi-symmetric good? Quasi-symmetric is good because these maps admit a quasi-conformal extension to the disk. These maps, these our map phi conjugating, say, z to the 5 or the Blaschke product B to the Bowen series map A associated with S04. This is a circle map. It does not admit a quasi-conformal extension to the disk, but it admits a Wied extension to the disk. And then, once you know that, so this is a theorem. This is a theorem. This is the theorem by, I only remember Sergey right now. Who else? I should start with Lubitsch. No, Dalap. No, this, in this particular case, maybe I should, Dimitrios, yeah. Okay. So Russell was a special case. But anyway, let me write everything. Large, Lubitsch, Erenkov. Let's see, don't tell me. Is that right? Great, okay. Right, so Russell, Lodge, Misha Lubitsch, Sergey, and joint work with Dimitrios Zala, because it's not a 5-author paper, it's a 2 different papers, but I just put them together. It was proved first in a special case with a work with Misha, Russell, and Sergey, and then later generalized in this paper. It actually proves some general kind of welding result, that's maps conjugating a large class of expanding dynamical systems to expansive dynamical systems, allowing hyperbolicity to go to parabolicity, are welding homeomorphisms. Okay, fine. So then I have solved, let's see, maybe I want to keep this. So I have solved my equivariant welding problem. And what I have done is I have constructed a conformal dynamical system, right? So I have taken this as the lower hemisphere, let's say, and taken that as the upper hemisphere, glued them, uniformized it. The circle has in the process become something that's no longer a quasi-circle. It will have cusps. So let me try to draw it this way. So remember, the Bowen series map is not defined on the whole disk. It's a piecewise Mobius map. It is only defined on these pockets, on these finitely many hyperbolic half planes. So my map is now defined in the interior of this pink curve. Inside, I have the Blaschke product action. So I have a complex analytic map. Let's call this domain D. Omega is the topological disk. Let me just say what this conformal mating is. What do we really get? So omega is the topological disk bounded by the pink curve. When you glue two Blaschke products, you get a map that's defined on the whole circle, on the whole sphere, and you immediately have this algebraicity property that a map on the whole sphere, if it is holomorphic, it is an algebraic map. It's a rational map. Same thing is true for in the Kleinian group setting. When you uniformize and you get conformal automorphisms defined on the whole sphere, it all sounds very trivial that magically, but if you think about it, it suddenly becomes a conformal object suddenly becomes an algebraic object. This exact thing is going to be problematic for us. But let's see what we get. We get a map F from the closure of omega to the sphere. It is continuous, meromorphic on the interior, on the domain omega. And there is this, actually there are cusps. Let me see if I can draw this slightly better. So there are cusps on this limit set. Anyway, the white thing is the limit set. The dynamics of the map F on the inner region, omega minus, let's say, is conformally conjugate to the Blaschke product. This is exactly like the quasi-Blaschke situation. You have a Jordan curve that is invariant. The dynamics inside is conformally conjugate to the Blaschke product. The dynamics outside is conformally conjugate to the Bowen series map. But now it's not quite defined on the whole disk. It's defined wherever it is defined, right? It's defined outside that fundamental domain pi. So this map is a complex analytic combination. So remember the reason why I could even construct some object that mimics, that captures the joint behavior of a Blaschke product and a genus zero Fuchsian group is because of the passage from the group to the map, and the map turned out to be topologically the same, and then we managed to solve the analytic equivariant welding problem. But that only gave me, what does it give me? It gives me an analytic map defined on a subset of the sphere. How do I even go from this analytic map? You can stop here if you're happy to get some sort of an analytic combination of a map of a group where you don't quite see the full structure of a group, but you see some partial structure of the group. If you stop here, then you're happy. But if you ask, what about the original goal? What about the goal where I wanted to go to a correspondence? Then you got to understand what this map F is. What kind of an analytic map is it? And what do I know about this map? All I know at this point, almost nothing. It's just a meromorphic map extending continuously to the boundary. Obviously, this map does not extend global analytic continuation to the sphere, because if the map extended in a neighborhood of this point, then the Bowen series map, which is lost in space. Thank you. Then the Bowen series map will extend analytically in a neighborhood of this kind of a cusp, which is not the case because you have some Mobius map here and a different Mobius map there. You cannot have an analytic continuation in this neighborhood. So that's why the map does not extend to a neighborhood. So this map is really not a global map of the sphere. So how do I even try to give some kind of an analytic, precise description of this map? So the point is, there's something that I know about this map, very little, but this is what I know. The Bowen series map was defined as gamma 1 on this orange curve and gamma 1 inverse on this orange curve. And so the map basically sent this orange curve to this one. Some point P here went to gamma 1 of P. Then you apply the map again. The map is gamma 1 inverse, so gamma 1 P comes back to P. So the map is an involution on the boundary. And that's what I know here. This pink curve, maybe I should have drawn in orange because that's exactly what it corresponds to, the boundary of the fundamental domain. So this is what I know, that the map F restricted to the boundary of its domain of definition is an involution. Its second iterate is the identity map. And I claim that any map which has this property, namely, say take a topological disk. It's not important to take a topological disk, but let's stick to a topological disk here. You have a topological disk with piecewise nice non-singular boundary, piecewise non-singular real analytic boundary. So mostly real analytic with some singular points maybe. And you have a map that's continuous, meromorphic on the domain, continuously extends to the boundary, and it's an involution on the boundary. Then F is an algebraic function. And it admits an explicit description. What is that explicit description? What I want to do is, so this basically solves two problems in the same time. I'm going to give an explicit algebraic description so that I'm slightly happier. Secondly, there's a problem with this particular map. The problem is that if you look at the Bowen series map, there's a tiling here, right? Gamma 2 will send you from here to there, and the map stops. The map cannot be iterated forever. Every point eventually maps to the fundamental domain, and then dynamic stops. And that's a little problematic if I want to construct some sort of a dynamical system. Maybe I don't want an escaping set like this. So what I want to do is, I want to solve these two problems at the same time by taking two copies of this domain omega. Did I call them omega plus, omega minus? Maybe that was not a good notation, because these omega plus and omega minus were basically, I should have called this is the limit set lambda, and I have the interior of lambda and exterior of lambda. So lambda plus is the exterior of the white set, the limit set, and lambda minus is the interior of the limit set. Okay, now I want to take two copies of omega. Omega plus and omega minus, two copies of the same thing. I'm going to glue them together along their boundary using the map S. I know, or F. So F from the boundary to itself is an orientation reversing because that's how fundamental domain works. If you go from here to there, the side pairing will go like this. Piecewise analytic map. And as such, I can weld these two objects. I have two copies. It's basically just a welding construction. I have two copies of the same thing. I'm taking a point on the boundary of the first copy, identifying it to the a point on the boundary of the second copy if the point P here is identified with the point F of P on the boundary. So point P on the boundary of the first copy is identified with the point F of P on the boundary of the second copy. You can ask, if you're alert, you can ask, well, this map is not quite analytic everywhere. So how do you know that the Riemann surface that you get by welding these two objects is actually a Riemann sphere? Maybe these points, when you weld them, become holes. The extremal length may not go to 0 around them. So that requires some work, but it turns out that the welded surface, you take these two, do the welding via S, is a, or can be given the structure of a compact Riemann surface, in this particular case, a Riemann sphere. And maybe I'll just, I anyway started, how many minutes late did I start?
So we started at 23. So
23.
10,
Okay.
23.
Okay, sounds good. Okay. So I put these two things together.
Five
Okay.
more minutes.
Thank you, you're very kind. So I'll take these two things, these two domains, put them on top of each other by gluing under S, and that gives me some Riemann sphere. What do I want to draw? Maybe I want to draw the orange curve, which is what two copies were glued along. So there's some orange curve here. This is my compact Riemann surface sigma sphere in this case, but in general, of course, if the region omega is not simply connected, then this would become a higher genus Riemann surface. And you have a copy of omega plus here and a copy of omega minus there. At the moment, maybe it looked like a bit unrelated to the conformal mating S. Here I have the conformal mating, which was this is where the map S lives. I want to construct, so I want an algebraic description for this map. I have the first thing is I have found a compact Riemann surface. A compact Riemann surface is almost an algebraic object, but I also want some sort of a map on it. I want a meromorphic map from here to there, and I want to write my map S in terms of this. So first observation is that since I glued two copies of the same thing using an involution, there's a natural pairing of the top and the bottom. There's a natural involution eta. That's the first map on this compact Riemann surface. The top and the bottom can be identified. Secondly, I want to define a meromorphic map here, which acts as identity on the bottom, and the top, the top is basically nothing but the domain of definition conformally. So here I want to define the map as S. They match up due to the involution structure of the map S, and turns out that R is a meromorphic map from the Riemann sphere to the Riemann sphere, and hence it's a rational map. And finally, the map S, the way we define the map R as identity at the bottom and S on the top, it turns out that S, which is defined on omega, has a very simple description. Let me just write it down. Put maybe a tilde here because these are not exactly the same. Well, no, that's fine. These are the two copies. Okay, fine. Okay, so what is it? The map S, what is it? See, the action of S is actually built in the definition of the map R. So the way S acts over here is first you go from here to the bottom copy, then you have to go identify this with the top one, and that's where S acts. That's how R was defined, as S over here. So the map S is now defined in terms of, the exact formula is not important, but it's defined in terms of this involution and this rational map. And this gives you an explicit rational, explicit algebraic correspondence. And all you need to do is to lift the dynamics of the map S by this uniformizing rational map. What do I mean by that? Well, if you have a point here, you want to send it to some number of points. It's a multi-valued map that you want. So first send it to here. You want to say that a blue point goes to a red point. So Z goes to W provided R of Z goes to R of W. And this gives you a multi-valued map here. It turns out that this is a holomorphic correspondence, and this particular holomorphic correspondence combines the action of the Blaschke product and this genus 0 orbifold, the punctured sphere group, simply because on this side I do have the action of the Blaschke product inside and the action of the Bowen series map outside. when you lift it to the correspondence, you see the full structure of the punctured sphere group on the correspondence and the Blaschke product action. Some branch of the correspondence will then behave like the Blaschke product. Okay. This, let me just conclude by saying, this allows you to, so by the way, you have a Riemann sphere, and on the Riemann sphere, the involution can always be taken as 1 over z. So essentially, these correspondences are parameterized by the rational maps R, and you don't have to work with a single Blaschke product and a single Fuchsian group. What it gives you is a combination, so it also unifies the space of Blaschke product and the space of Fuchsian group. So you have an embedding of the product of the space of Blaschke products of a certain degree and the Teichmüller space of punctured spheres into the space of correspondences. And if you do it, and then of course you can ask for all kinds of questions. What is the boundary? So if you fix the Blaschke product side and look at the embedding of the Teichmüller space in the space of correspondences, you can ask whether it's pre-compact, what are the boundary correspondences, is the boundary of this particular copy of the Teichmüller space in some natural sense similar to the Bayes boundary, etc. Everything that you can ask about the Teichmüller space can be asked in this setting. And more generally, if you are a little more creative and instead of working with a single Blaschke product and a single Fuchsian group, it's also possible to do this for a collection of Blaschke products and a collection of genus 0 orbifold groups. I only showed it for the punctured sphere, but this actually works for modular group and Hecke groups as well. But the upshot is that if you do that, in general, the correspondences that you get will not live on the Riemann sphere, because omega may be multiply connected, and if omega is multiply connected, you stack one copy of that on another, and you get an arbitrary genus G surface, which turns out to be hyperelliptic because of this particular involution. And you get a correspondence on this arbitrary genus G hyperelliptic Riemann surface that combines the action of finitely many Fuchsian genus 0 orbifold groups with finitely many Blaschke products. And now you have a very interesting object, I think, about which I think nothing is known. You have a map from a product of finitely many Blaschke product spaces and finitely many Teichmüller spaces into what's known as the Hurwitz space. You have a space, you have a sphere, sorry, in this case, you had a sphere. In general, it could be any point in the moduli space of genus G surfaces, and this could be any meromorphic map. So you have an embedding of these conformal dynamical systems, Blaschke products, Fuchsian groups, product of them into this algebraic Hurwitz space. And I think it's very interesting to try to figure out what sort of embedding this is, and one can ask a lot of questions. Okay, I'll stop. Thank you.